Welcome to the second lecture in Unit 6, the Earth's Dynamic Atmosphere. In this chapter, lecture will be covering Chapter 17, Moisture, Clouds, and Precipitation. So the most important thing you need to know or think about when you're considering how water interacts with the atmosphere, that is the layer of gas that surrounds the Earth, and water can take a gas form, or the gaseous phase of water. This is water vapor. Really important thing to consider or to keep in mind when you're talking about water is that when water changes state, heat energy is absorbed or released. Remember, we talked a little bit in the previous chapter about energy, electromagnetic radiation, and heat in particular, how things that are cold are lacking in heat energy and things that are warm have abundant heat energy. It's not that coldness, quote unquote, is something specific and hotness is also something specific, a quantity that is different. It's really a lack of heat energy or an abundance of heat energy that defines whether something is cold or warm. Water molecules have a tremendous heat capacity, or a relatively high heat capacity. And water can take several forms. It can be solid, liquid, or gas, otherwise known as vapor. Water molecules, when they're frozen as ice, or their solid form or solid phase, they're bonded together in a configuration that has a lot of empty space, relatively a lot of empty space relative to liquid. Certainly they doesn't have more empty space than in gas form, but a solid form, less empty space in liquid water than in solid water or ice, and that's why ice is less dense and it floats. When ice melts, it takes about 80 calories of energy. Calories is a calorie is a unit of energy. Melting takes about 80 calories. Freezing releases 80 calories of heat energy. When liquid water evaporates, it takes about 600 calories of heat energy to evaporate 1 gram of water. And conversely, when water is condensing or going from gas to liquid phase, it takes an equal amount of energy. The point here is that for water to change phase, either requires energy absorption or it requires energy release, or it results in energy release. And there are other two-phase state changes of water that you can skip this kind of water phase hydrologic cycle. You can skip the middle zone of liquid and go straight from solid to gas, which is a process called sublimation. And you can see that when you go from solid to gas, you need about 680 calories of energy to make that phase transition, which is the sum of the melting energy as well as the evaporation energy. And when gas goes from gas phase, or water vapor goes from gas phase to solid phase, conversely, it requires about 680 calories per gram of water for that. Now, condensation takes 600 and freezing takes 800 or 80. Deposition, which is gas to solid directly, is the sum of those two processes. Again, the takeaway from here is that water changing phase takes energy or releases energy. Humidity is the amount of water vapor contained in a volume of air. Saturated air is air in the atmosphere that is filled or that has as much water vapor as it can hold. Now, there is always, like a sponge, there's only so much water a sponge can hold before it will no longer soak up water. Or if you think back to groundwater, the groundwater unit in this course, there's only so much volume, there's only so much empty space in, say, a rock layer, in a rock unit that can hold liquid water. That's its porosity. Remember, permeability was the rate at which it transmits water. Porosity is the amount of void space, the amount of empty space that can hold water. You can think of air as in a similar fashion. That is, there's enough molecular or chemical space in air to hold other things, such as water vapor. But there is a point at which there is no more room. So saturated air is water vapor that has as much water vapor as the air mass can hold. The capacity, or this saturation state, is temperature dependent. That is, warm air has a much greater capacity to hold more water than cooler air does. And water vapor adds pressure it's called vapor pressure to the air. What's interesting, it doesn't add atmospheric pressure. I should rephrase that. It does add atmospheric pressure, that is the weight of air above any point on Earth. However, water is an interesting molecule in that a water molecule is made up of hydrogen, 2 hydrogens and 1 oxygen, which has a molecular mass of 18 units. Let's just talk about that. So we'll just use a general term. It has a mass of 18. Nitrogen, on the other hand, is a molecule that's made up of 2 nitrogens, and it has a mass of 28 atomic units. Oxygen is mass 32, has a weight of 32 atomic units. So you can see that water actually weighs less than a molecule of water weighs less than a molecule of nitrogen or a molecule of oxygen. So when water vapor goes into the atmosphere, it actually kind of displaces some of the air, some of the oxygen and nitrogen that is in that space, and actually causes a reduction in the atmospheric pressure of that column of air above a certain point. But switching back to this slide, the amount of water that goes into the air has what's called a vapor pressure. That is, it exerts a outward force around the molecules of water. Now, relative humidity can change at temperature, or relative humidity can change at a constant temperature if you add more water to a system, to a vapor, or to an atmosphere, or it can also change with increasing or decreasing temperature with a standard amount of water in that mass. Humidity is measured or discussed, contextualized in terms of what's called relative humidity. That is the ratio of the amount of actual water vapor in an air mass compared to the amount of water vapor that the air mass could hold. That is its capacity or the saturation state. Relative humidity is expressed as a percent. And when an air mass is saturated, it means that its content equals its capacity. So remember, air temperature goes up, capacity goes up. Air temperature goes down, capacity goes down. As the amount of water vapor in a mass of air goes up, the amount that can be added until it reaches capacity goes down as well. So saturated air is defined as where an air mass, the content of water vapor in an air mass equals the capacity. And that would be 100% relative humidity. Something that is 50% relative humidity would have 50% of the water that air mass could hold. Relative humidity can be changed in 2 ways. You can either add or subtract moisture from the air. If you add moisture, it raises the relative humidity, and if you remove moisture, it lowers it. Or you can change the air temperature. Remember, lowering the temperature raises the relative humidity so that for a given amount of air, or a given amount of water vapor in air, if you lower the temperature, the relative humidity or the capacity, the relative humidity goes up and the capacity goes down, or the remaining capacity goes down. And the dew point temperature is something you sometimes see in nightly news reports. It's the temperature to which a parcel of air that has water vapor in it would need to be cooled to reach saturation. When air cools below that dew point, it means that the air becomes saturated and water has to turn from vapor into liquid water. That's when you get dew, fog, or cloud formation. But water vapor does require a surface to condense on. And remember, in that last chapter of atmospheric composition, we talked a little bit about aerosols. These are particulates, either solid or liquid, that exist in the atmosphere, and those make fine surfaces or condensation surfaces for water to condense on, or what's referred to as nucleate. They go from gas to liquid. Daily variation in temperature and humidity follows these patterns that we just discussed. That is, when you have the lower temperatures for a given kind of water vapor content in a mass of air will result in a higher relative humidity. And you can see these plots are out of phase. That is, this plot of temperature throughout a day from 12 midnight through noon to midnight the next day. Same plot down here. You track the temperature. This plot isn't for a particular place or time, but it's pretty typical of most places on Earth, where at night temperature goes down because you have less solar radiation, and during the day, as solar radiation increases, you reach a maximum temperature kind of late in the afternoon, which then drops down as the sun sets and darkness prevails. You can see as your minimum temperature early in the morning, before the sun's solar radiations really had a chance to warm up the Earth, the lowest temperature point actually has the highest relative humidity, typically because the capacity of that air mass for water is the lowest. So any water vapor that's there is relatively closer to the capacity point than it would be otherwise. And when your air temperature goes up and you have the highest capacity for water, that same amount of water vapor, that same mass of water vapor, is relatively low in terms of its share of the capacity that air mass can hold. Another process that affects moisture in the air, in the atmosphere, is something called adiabatic heating and cooling. Adiabatic temperature changes occur when either air is compressed or air expands. It doesn't require the addition and removal of heat energy. Rather, it is the change in density of heat energy in a body or in a mass based on its expansion or contraction. And so as air warms, as air masses descend closer to the surface of the Earth, remember there's 50% of the mass of the atmosphere is under a few kilometers in height. As air masses descend, they become higher, more pressurized due to the weight of molecules above them in that column of air. And as it descends, it compresses. And this compression causes warming of that air mass. Conversely, as air rises due to either convective forces or horizontal forces that cause air masses to move aloft, air expands, density becomes less. Air pressure or density related to air pressure is that the air pressure, the weight of the atmosphere above that air mass is reduced as it goes higher and higher and higher away from the surface of the Earth, and it expands. And as it expands, you get what's called adiabatic cooling. And so the energy state of that air mass is cooler and goes down. The adiabatic heating and cooling in the vertical dimension, there are two zones of adiabatic cooling. The dry adiabatic zone, which is where the dry adiabatic rate occurs. This is where air is warm enough that it is generally undersaturated or not at its full capacity. It's at relative humidity lower than 100%. The dry adiabatic rate causes air masses to cool at a rate of about 10 degrees C per 1,000 meters. All the way to about 2 degrees C at generally 3,000 meters aloft. You switch into the zone where relative humidity is close to or at saturation, and the wet adiabatic rate occurs as it continues to rise, which is a temperature drop of about 5 degrees C per 1,000 meters. Another process through which air is moved aloft is something called orographic lifting. And that's a little bit more intuitive to most people. And that is, as dry air or wet air, doesn't really matter, wet or dry, it's kind of all part of the same continuum in the spectrum. As air moves laterally across a land surface, it's typically heated or contains some moisture. But when it hits a barrier, that is, say, a mountain range or any kind of large geomorphologic feature, any large feature on Earth, that air is unable to continue to transmit along horizontally, and it's lifted. As orographic lifting takes place, as we saw in the previous slide, what you get is cooling due to the adiabatic cooling process that occurs in air masses as they're raised up higher, as they move aloft. Subsequently, air temperatures or the temperature of that air mass drops. We know what happens when the temperature of an air mass drops. Its relative humidity tends to go up, and when it reaches saturation, water is forced out. It is forced to condense and nucleate. This often results in what are called rain shadow deserts. That is, in mountain ranges near coastal environments where wet air may be moving horizontally across, in this case moving left to right across. As that air mass is moved up, the water and condensation falls out. When it reaches a high altitude point, as that air mass continues to move across that geomorphologic feature and comes back down to its original altitude as it comes over the backside of a mountain range over here, It comes down. We know when air descends, it tends to warm. It's lost a lot of its moisture. Warming air has more capacity, or is undersaturated by a large degree relative to cooler air, and you have very, very dry air on the backside of mountain ranges. So essentially, put in simpler terms, wet air moves across. When it goes up in altitude over a mountain range, it rains on the front side with all the moisture that was in it that incorporated from over the marine system. It rains, all of that moisture leaves the air mass system, and that air mass system continues back over the backside of a mountain range, drops down where its saturation state and relative humidity are quite low, resulting in a desert. Another way in which air masses move aloft are due to not physical barriers, well, not landform or geologic barriers to air movement, but are due to air mass barriers, that is fronts, cold air and warm air. Warm air is less dense, tends to move aloft relative to cool, denser air. You can think of this in similar terms as you do in continental subduction. Plates that are denser subduct below plates that are not as dense. This is the same idea. That is, warm air is less dense than cool air. And so when a warm air mass comes in contact with a cold air mass, the warm air mass rises above. The cold air doesn't subduct into the earth, but it does subduct below the warm air mass. Cool air can act as a barrier, and frontal wedging. Fronts are part of storm systems in mid-latitude cyclones, which we'll address in a future chapter. Convergence is where air is flowing together, and you have rising air. A third way in which air masses can move aloft and move vertically in the atmosphere are due to a process called localized convective lifting, and that is basically due to solar heating that is concentrated in an area, either due to cloud formation adjacent, and you have a patch of area that is not covered in clouds. Localized convective lifting occurs when unequal surface heating causes pockets of air to warm and therefore rise because they're less dense than the surrounding air. This is what are called or referred to often in terms of thermals. Soaring birds and people who love to hang glide and fly gliders love to find thermals. These are rising currents of air that can be relatively small, on the order of tens to hundreds of feet to kilometers in nature. And rising thermals, when they reach that transition between the dry adiabatic zone, the dry adiabatic rate, and the wet adiabatic rate, where saturation state reaches 100% humidity, you get condensation and cloud formation. Now, air that is considered stable is air that resists vertical displacement. So usually stable air is thought of to be, stable air in general is cooler and denser than surrounding air. Means it's kind of wants to stick where it is. Is not subject to adiabatic cooling because it's stable in the vertical dimension, that is, doesn't really rise. Absolute stability is a concept or a characteristic that occurs when the environmental lapse rate, that is, the rate of vertical cooling, is less than the wet adiabatic rate. And stable air often results in widespread clouds with fairly little vertical thickness. That is, these are the kind of wispy clouds where there's a very, very kind of fine transition zone. Rarely precipitation, because cloud formation, again, is relatively minor. Unstable air, on the other hand, is an air mass that tends to rise, and that's due to either the localized convective lifting, orographic effects, or frontal wedging. And it's warmer air than surrounding air. It's less dense because it's warmer, and it continues to rise until it reaches equilibrium with surrounding air, that is, it reaches an altitude with the same temperature. Adiabatic cooling happens in unstable air masses. The lapse rate is greater than the dry adiabatic rate, and you often find very, very thick layers of clouds that have the potential for large amounts of precipitation. Conditional instability, compared to absolute instability, occurs when the atmosphere is stable for an unsaturated parcel of air, but unstable for a saturated parcel, and that's in a frontal environment where cold air tends to be stable and immobile, whereas a wedging effect occurs, and an unstable air mass is going to be pushed aloft. So air stability is really what determines the type of clouds that develop and the intensity of storms and precipitation that can occur at those transition zones. Condensation and cloud formation are the processes that ultimately determine how the atmosphere interacts with the hydrosphere, hydrologic cycle, and the geosphere and the biosphere in terms of precipitation. Condensation is the process by which water vapor in the air changes to liquid and forms either dew, fog, or clouds. Condensation has to occur on a surface. Condensation surfaces on the ground can be any kind of physical hard surface, grass, car window. When you walk outside early on a cool but humid day, you'll get condensation on your body. But the atmosphere also has plenty of condensation surfaces, which are considered condensation nuclei. It's a place for condensation to nucleate. Dust and smoke are condensation surfaces. Ocean salt crystals are nucleation surfaces. Aerosols, as we mentioned in the last chapter, are nucleation surfaces. Clouds are made up of condensate. That is, when water condenses in the atmosphere, it has the potential to form clouds. And clouds are made up of millions of tiny water droplets or tiny crystals of ice. These are nucleated water droplets of condensation. Clouds can be classified several different ways. Height is one way in which scientists classify clouds. Again, it's just to set up a vocabulary so that scientists can discuss them. And really the name of the clouds is sometimes less important than really what they mean, but nonetheless, you can't really converse with other people about a phenomenon, a natural phenomenon, without having common terms that are used to describe what is being discussed. So in terms of height, there are high, middle, and low clouds. High clouds are considered to exist above 6,000 meters. Cirrus, cirrostratus, and cirrocumulus clouds are these high-altitude clouds. You see the wispy cirrostratus and cirrus oftentimes in Florida on pretty clear days. If you squint, you can see these wispy zones of condensation. And cirrocumulus occur at really pretty high altitude as well. Middle clouds, the altostratus and altocumulus, are also fairly common, especially altostratus in the Panhandle or in the Florida Peninsula. Lower clouds, which are 2,000 meters or below, stratus, stratocumulus, and nimbostratus. Nimbus, by the way, indicates a rainy component. And then there are clouds that kind of transit, that go from low into the middle, and can sometimes even approach the high zone. And cumulonimbus are these, and those are probably the most common that we think of in Florida. These are thunderheads, or they often produce pretty violent storms. They're due to rapid movement, vertical movement of humid air aloft. But the three basic forms are cirrus, cumulus, and stratus. Nimbus, remember, is rainy. So cirrus are high clouds. See, when anything that's super, super high, you can consider it a form of cirro or cirrus. The cumulus types are globular, so that just describes the form as well. Kind of rounded masses, often associated with fair weather or good weather. And stratus clouds, which, remembering back to the earlier units on geology, stratus has the same root as strata. These are sheets or layers. So if you think of stratigraphic or strata in rocks, and you think of stratus clouds, you can think that they're the same. They're relatively planar or sheet-like clouds that can cover wide expanses of the atmosphere. Now, fog is basically a cloud that has its base at or near the ground. It's considered an atmospheric hazard because it can affect human transportation systems. dramatically. Most fogs form because of radiation cooling or movement of air over a cold surface, that is, changing the saturation state or the capacity of an air mass with respect to its water content due to temperature changes. Fogs caused by cooling are advection or radiation or upslope fog. These are three types of fog that occur when warm, moist air either moves over a cool surface or loses heat very rapidly, or is subject to orographic cooling. That is the vertical displacement of a humid air mass up and over, say, a mountain range. Evaporation fogs, on the other hand, are where air masses with a particular humidity or water content character move over areas where evaporation is occurring. So if cool air moves over warm water, and that warm water is evaporating, that moisture is added to the air, which, being cool, doesn't have a high capacity for it, and fog can develop. Frontal fog or precipitation is the same. When warm air moves over colder air, the warm air that has a relatively high water content and relatively low relative humidity, all of a sudden that high moisture air is cooled suddenly by the proximal or proximity to the colder air mass below, and rain evaporates and forms fog. Now, condensation nucleation processes vary over or work over a wide variety of sizes, or a wide range of sizes. Condensation nuclei are the particles, the atmospheric particles that can form the basis or form the structure on which water can condense, can be very, very, very small. As small as 0.0002 millimeters. Another way of saying that would be 0.2 micrometers, or 200 picometers. These are really, really, really small particles. Aerosols, you can imagine that aerosols, these are solid particles that are floating in the atmosphere, are probably pretty small like that. Cloud or droplets or water that can nucleate and build on these small nucleation surfaces can be anywhere from 20 micrometers, or 0.02 millimeters, to 50 micrometers, or 0.05 millimeters. You can see a typical human hair in this graphic is roughly 0.1 millimeter, or 100 microns. That is double the size of a cloud droplet. And a rain droplet is 2 millimeters, give or take. That is about 20 of these large cloud droplets would combine to form a typical raindrop. Precipitation, which is the movement of condensate or atmospheric condensed water downward by gravity, can take place two different ways. The Bergeron process occurs when temperature in the environment where nucleation is taking place is below freezing. Ice crystals collect water vapor, and large snowflakes form and fall to the ground, or melt during descent and fall as rain. But Bergeron process is exactly or is limited to low temperatures, and it's how snow crystals and snowflakes form. The collision coalescence process occurs in warm clouds where large hydroscopic condensation nuclei. Now, hydroscopic or hygroscopic, you could say it hydroscopic too, means that hydroscopic or a hygroscopic condensation nuclei is a nuclei that really kind of wants to soak up, has a high affinity for liquid water. It attracts water. Collision coalescence processes require a large hydroscopic surface. Large droplets form, and droplets collide with other droplets during their descent to make quite large raindrops. And common in the tropics, if you're used to tropical and subtropical monsoon, you know the droplets seem to be much larger than they do in places where it's more of a misty kind of northern or higher latitude rain. Formation or forms of precipitation. This graphic on the right here shows the typical collision coalescence process, where you have these large cloud droplets, again 50 microns in diameter, start to interact with others, and as raindrops fall, they hit more cloud droplets, and you get these very, very large raindrops, which can then fragment again into smaller drops and as they move through vertical space. Forms of precipitation are, again, fairly intuitive to most students. Rain and drizzle are characterized by the droplet size. Snow is characterized by its form and temperature, or its form and state, I should say. Its form as in crystals, and its and state as solid. Sleet and glaze are kind of in between. Sleet is it's a wintertime phenomena when rain freezes into ice crystals as it falls down. Glaze or freezing rain is when rain falls on a surface that is sub-zero or frozen and causes it to freeze on that surface. Some other forms of precipitation are hail that occurs when updrafting thunderheads and down traveling raindrops or ice nuclei are falling, and they zigzag through a cloud formation, picking or becoming liquid and freezing, liquid freezing, liquid freezing, picking up and growing. Oftentimes you can see if they're in their cross section, you can see the layers as they have moved through this system, building layer upon layer before they have enough mass that they actually are able to penetrate the updraft and get down to the surface. And rime is when condensation forms directly on cold surfaces. It's almost a form of deposition. That is, in that initial slide on chapter 16. It's almost a form of where going from water vapor to solid right away, and you get really kind of delicate features of ice freezing on solid nucleation surfaces on the surface of the Earth. Scientists measure precipitation several different ways, but the most common and simple way is to use what's called a rain gauge. Rain is the easiest to measure because measuring instruments are relatively standardized. Wind currents that can blow snow around and either cause them to enter collection vessels or not are relatively or have less impact when it comes to rain. Standard rain gauge uses a funnel that collects rain falling down, and the funnel may be wider than the actual tube in which it's collected. However, the surface area of this is accounted for in the vertical scale of the rain gauge. Snow can be measured two different ways, either by depth or water equivalent. Depth, if anyone who's from the north or has experience with snow knows that some snowstorms are pretty wet, or some snows are pretty wet and dense, and some are pretty dry and fluffy, and they can represent similar amounts of actual snow. You can have a snowstorm that lays down 2 inches of really, really wet, soggy snow, and a snowstorm that deposits, a foot or more of real fluffy white or fluffy and light snow. However, the amount of water contained in those two snows could be about the same. It all depends on the density and the nature of the molecules or nature of the crystals that are being accumulated. So that's the end of chapter 17. As you noticed, I'm trying to move a lot faster, especially for this unit. It's a big one. So we'll see you in the next chapter, chapter 18.